Okay, good morning, everyone. Welcome back. So first, let me make an announcement. So this week, because Wednesday is a well-being day of the university, so we will have no lecture on Wednesday. So this week, we only have one lecture. And also because of the well-being day, I will post this work's homework on Monday instead of Wednesday. Okay. The due date of the fifth homework will be next week. It will still be Wednesday next week. And the due date of the fourth problem set that is due this week will be deferred to Thursday because of the well-being day on Wednesday. Okay, so let's go back to our lecture. So last time we did a quick review and a quick summary about the principle of the least action. Okay? So we showed that we reviewed that in classical mechanics, once we write down the Lagrangian of a system, we can do a time interval and get the action. And once we know the action, we can use the principle of the least action, which means the variation of the action equals 0. Okay? We can use this principle of least action to immediately write down the equation of motion. And the equation of motion is this guy in general, where Q is a coordinate of our system, and the Q dot is the time derivative of coordinate, which is our velocity. Okay, so that is what we reviewed last time. And last time we also give one example, which is a pendulum. So we said that there is a pendulum with a rod length r and mass m, and we use angle theta to be our coordinate, and the time derivative of theta is our velocity. And we write down the Lagrangian, and we use the variation principle to get the equation of motion, and we find that this equation of motion is exactly what we expect from the second law of Newton. Okay. There is one more thing I would like to mention about classical mechanics before we go back to ENM. That is the choice of coordinates. So for example, for this pendulum problem, in our previous lecture, we use this angle theta as my coordinate. I use the theta to describe the location of my pendulum, the configuration of my pendulum. But this is not the only choice. We can have other options. For example, I can use the xy coordinate of my mass, m, to be my coordinates. Okay, so this let me horizontal axis is x, vertical axis is y. I can use the location of this point mass xy as my coordinate. Okay, so that is also a possible option. Theta or xy both gives me the configuration of this pendulum. However, for this particular pendulum problem, this theta coordinate is much better than xy. Okay, the reason this theta use theta as a coordinate is much better is because this theta is a so-called unconstrained coordinate. In other words, this value of theta can be anywhere. This theta can take any value. I don't have any constraint on the value that theta could take. Okay. However, if we choose xy as our coordinate, then this xy need to satisfy a constraint. That is x squared plus y squared need to equal to r squared. So here I choose the this end to be my origin. Let's say this one is 0, 0. Okay. If that is the case, then the location of my point mass need to be distance r away from the origin. So I need to satisfy the constraint x squared plus y squared equals r squared. In other words, x and y are not independent degrees freedom. If I know x, y is already fixed. If I know y, x is already fixed because I know my distance of my point mass to the other end of my pendulum need to be r. Okay, so this xy coordinate is a so-called coordinate with a constraint, and the constraint is x squared plus y squared need to equals r squared, which means the rod length is r, they cannot change. Okay. If we use a constraint, a coordinate with constraint like x and y as our coordinate, then we can still do Lagrangian, and we can still write down Lagrangian. This will be our Lagrangian using the xy coordinate. The only difference here is the velocity. Now it's not just theta dot; it contains x dot and y dot. Okay, so x dot is a velocity along x direction, y dot is velocity along y direction. So we square them and add them together is the kinetic energy. Potential energy is mgy. Okay, you know, this coordinate is okay. We can still use this coordinate to write down Lagrangian. However, we can't just simply do the variation principle for this Lagrangian and get the equation of motion. If we naively treat the xy as our coordinates and do a variation for the action, we will find some wrong equation of motion. This equation of motion will be wrong. Okay, and the reason this equation of motion is wrong is because, as I just mentioned, x and y are not independent degree of freedom. There is a constraint between x and y. They need to satisfy. Okay, so using constraint coordinates is usually not a good option. We cannot naively do the variation principle. Okay, using constraint coordinate is still okay. There's still a way to do that, but that will be much more complicated. So this section, by the way, is optional section. If you are interested in this part, you can look at it, but it's not required. So this section basically demonstrates to you, if you use a constraint coordinate, x squared plus y squared equals r squared, okay, you choose xy coordinate, and this coordinate need to obey a constraint. If you have a coordinate that need to obey a constraint, what should we do? That is demonstrated in this section. Okay, and the bottom line is, if you use coordinate with a constraint and try to solve the equation of motion using Lagrangian and variation principle, it is still doable. But instead of the simple Lagrangian, so this is the simple Lagrangian we had before, okay, kinetic energy minus potential energy. So instead of simple Lagrangian, you need to add one additional term. That term is a so-called Lagrangian multiplier. Okay, so this additional term is my constraint. So whatever constraint I can write down it as some function equals 0. Okay, so for every constraint I have, I need to multiply an unknown parameter lambda in front of that and added it to the Lagrangian. So my Lagrangian actually become more complicated because I need to add this constraint term. And once I add this constraint term, I got one more free parameter here is lambda. Okay, then I need to do variation principle for this whole thing. My original Lagrangian plus or minus this additional constraint term. Okay, and we need to do this variation for coordinate q, and we also need to do the variation for lambda for this Lagrangian multiplier. Okay, and this is the so-called constraint minimization. Okay, we try to get to the minimum, we try to minimize the action, but this action, the coordinate need to satisfy some constraints, and with constraints, this minimization needs to be handled by this additional Lagrangian multiplier. Okay, and as you can see, this is still doable, but everything becomes much more complicated. Equation of motion becomes much more complicated. A number of independent equations increase. Okay, at the end of the day, if we cancel everything, at the end of the day, we still get the same equation of motion. But as you can see here, this calculation is much more complicated. It takes much longer time to get the same equation of motion if we use the xy coordinates. The bottom line, when we choose coordinates in this Lagrangian description, we need to be very careful. Okay, it's much better to choose coordinates that do not have constraints. Okay, so this theta coordinate is much better because theta coordinate don't have a constraint. I can choose I can give whatever value to theta like using the computation. And this xy coordinate is not a very good choice. You can still use it, but if you use it, the minimization becomes much more complicated. You need to use Lagrangian multiplier, this mathematical trick, to handle the minimization, and the number of equations become increased, and the way to solve those equations become much more complicated. It takes much longer space. It's like almost one whole page to get the equation of motion. Where if you choose angle theta, it's just a one-line calculation. Okay, so the bottom line, we want to choose coordinates that don't have a constraint. If you use coordinate with a constraint, x squared plus y squared equals r squared with a constraint, things become much more complicated. Okay, so this is an important principle. It will guide us to choose the proper coordinates, to choose the most convenient coordinates that simplify our calculation. And we will come back to this principle later when we discuss about the E&M field. Okay, so I think that's all I want to say about classical mechanics. And now let's go back to E&M field. Okay, so for E&M field, so let's first look at some fundamental principles. Okay, so for E&M field, what we will do here is first, we will try to write down the action for the E&M field, as well as the, how does it couple to matter. Okay, And then we will use the vibration principle, delta S equals 0, to get the equation of motion and compare with what we learned in 505. Okay. So before we write down the action, so let's first discuss some fundamental principles. What this action would look like. Okay, what quantity this action will depend on. So first of all, this action should have 3 parts, okay, as we show here. The first part is EM. So that is the E and M field part, electro and magnetic field part. So this part of action depends on electric magnetic field, say E field, B field, the strength of E field, strength of B field, etc. Okay. The second part is a matter part, okay, because we know E and B field they does not come from nowhere. They come from charged particles, charged object, and the motion of charged object. So we need those charged objects to generate this E and B field. So the action must contain one part that describes the motion of those charged particles or charged objects. And in addition to that, this charged object and the E and B fields, they talk to each other, they couple together. Okay, so there should be a third term which tells us how does this charged particles and their motion couple with E and B field. Okay, and this couple term gives us 2 physics. One is how does the motion of E and B field generate, how does the motion of charged object generate E and B field? That comes from the coupling. Okay. And this coupling term also tells us if I have charged object inside the E and B field, what force do we get on this charged object? How does it move? Okay. So in general, we should have these 3 terms in my action. And of course, these 3 terms are different. They describe different part of the physics. So for the EM part, electromagnetic field part, this guy should depend on E field. It should depend on B. Or if we choose the scalar and the vector potential to describe E and B field, it should depend on the scalar potential phi and the vector potential A. Okay. And the matter field part. This matter field part should depend on, say, the coordinate of my charge object, the charge distribution. Okay, how does the charge distribute in my space? And how does the current distribute, current density in my space? So the matter field should depend on like quantities like charge density, current density, etc. It tells us the location of the charge, etc. Okay. And the coupling term should depend on both. Okay. The coupling term should depend on both E and B, or say phi and A, add rho and J. It tells us how does E and B, phi and J, phi and A couples with rho and J. Okay. So that is a basic principle. And as we will show later, this is indeed the case. Okay. And because we are doing E and M, okay, so in this course, we were mostly focused on the first term, the E and M term, and the last term, the coupling term. Okay. We sometimes will mention the matter term, but the matter term will not be our central focus, okay? Because the motion of the matter, how does matter change? The dynamics of matter is not part of E and M. Okay? So we are mostly focused on E and M, the E and M part and the coupling part. Okay? So this is because the E and M part contains E, B, phi A, the coupling part contains E, B, phi A, whereas the matter part doesn't contain E, B, phi A. So we are mostly focused on this guy and this guy, which contains my field. Okay, so that is a basic structure. Let me clear it. Okay, let's go to the next part. Okay, so this second part related with the choice of coordinates. Okay, so as we just mentioned at the beginning of this lecture, when we utilize this principle of least action, one very important choice or very important step is to choose the coordinate. Okay, so for our E and M, the action E and M, okay, we can choose to use E field and the B field to describe my E and M field. Okay, and we have another option. We can also choose scalar potential and vector potential to describe my E and M fields. Okay. As I mentioned early on, these 2 descriptions are pretty much equivalent to each other. We can use E and B field to describe my magnetic and electric field. We can use scalar and vector potential to describe the same physics, and it's basically option. Okay. So here, for the minimum, for the principle of the least action, if we want to use action, and we want to get the equation of motion from the action, which coordinate should we choose? Should we choose E and B, or should we choose phi and A to write down our theory, to write down our action? Okay. It turns out, so let me tell you the answer. It turns out phi and A is a much better option. Okay. The reason is because phi and A are the unconstrained coordinates, similar to the theta for the pendulum. Okay. So choosing phi and A is similar to choosing theta coordinates for the pendulum. And choosing E and B is similar to choosing the X and Y coordinates for the pendulum, where you have a constraint, X squared plus Y squared equals R squared. Okay. So to see that, we just need to go back to our Maxwell equation. So for example, in the Maxwell equation, we all know the divergent of B need to be 0. Okay. So if we use E and B, this is a constraint. So my Bx, By, Bz are not independent degree of freedom. If I know Bx and By, I can use this equation to get the Bz. So Bx, By, Bz are not independent degree of freedom. In other words, if I use B field as my coordinate, I need to add additional Lagrangian multiplier to take care of this constraint. Okay. And similarly, there is also some similar constraint on the electric field E, which I need to take care of if I use E and B as my coordinate. Where phi and A a much better option. Okay, so for phi and A, oops, sorry, this is a typo. This should be divergence of B. Sorry for that. I will correct this slightly later. So for phi and A, it's a much better option. As we discussed in earlier chapters, well, once we have phi and A, once we use phi and A to describe my electric magnetic field, this type of constraint is automatically satisfied. Okay? So for phi and A, we don't have additional constraints. Once we have phi and A to describe magnetic field, say, let me say, I say magnetic field is a curl of A. Okay? Once I do that assumption, the divergence of the magnetic field is guaranteed to be 0. So the constraint is automatically taken care of. So for phi and A, it's an unconstrained coordinate. I can write down the phi and A. I can give any value for phi and A, and they are independent degree of freedom. I can do whatever I want to them. But if I choose E and B, I need to satisfy certain constraints. And with constraints, it will make the vibration principle much more complicated. You need to use Lagrangian multiplier, etc. Okay. So the bottom line, because of the constraints, using phi and A is a much better option when we try to write down the action and when we try to get the equation of motion. Okay. So that's the principle of phi and A. So the story here is exactly the same as a pendulum. We want theta angle to describe pendulum. We don't want xy to describe pendulum. Here is exactly the same story. Okay, so the bottom line, when we write down the action for the EM part and the coupling part, we want to use scalar and the vector potential, and also charge density and current density to write down this action instead of E and B. Okay. Okay, so we can use E and B as the intermediate step, but at the end of the day, we should use phi and A. Okay, so that's the second point. And the third point is our old friend, the principle of locality. Okay. We have mentioned multiple times this principle is extremely important. Okay. And it gives us lots of deep insights about the physics, E and M field, all kinds of fields should satisfy. So what does the principle of locality tells us if we write down the action? So let me give you the answer, then I will explain slightly later. Okay. So this is the impact. The principle of locality tells me my action should look like this. Okay, so let me explain this formula a little bit. We know that the action is the integral of time of Lagrangian L. Okay, so L is our Lagrangian. Okay. And what the principle of locality tells me is that this Lagrangian L can be written as the spatial integral dx, dy, dz of curly L. And this curly L is what we call Lagrangian density. Okay? So this formula is actually pretty much the same as the relation between charge and the charge density. We know that if we have a continuum charge distribution, then the total charge of object is the spatial integral of charge density. Okay? So this integral basically tells me if I want to know the total charge of object, I can cut this object into small pieces. Okay, I can cut them into small pieces. And for each small piece, I know the charge density in that local region. Okay? And if you want to know the total charge of the entire system, I just add the local charge together. And adding this local charge together means that I need to do a spatial integral of the charge density and get total charge. Okay? So here for the Lagrangian, it's exactly the same story. The principle of locality tells me if I want to know the Lagrangian of my entire system, what I can do is I can look at each small area. So for each small area, I can define a Lagrangian density of this small area. If I want to know the Lagrangian of the entire system, I just need to do an integral. Integrate the Lagrangian density of each small area together. Okay? And the Lagrangian density is typically labeled as curly L. Curly L means it's a density. It's a Lagrangian density around the one spatial point. And then when we add all of them together, we get the total Lagrangian. Okay. So that is what this formula is indicating. Okay. So the Lagrangian is actually this integral. The spatial integral here is a spatial integral of Lagrangian density. And this spatial integral gives us the Lagrangian. And once we have the Lagrangian, we do another time integral. That gives me the action. Okay, so that's the principle of locality. And yeah, okay, so let me explain a little bit more about this principle of locality. Okay, so let me first explain a little bit more about what this Lagrangian density, curly L, will look like. Okay, so this curly L is a Lagrangian density, as I just mentioned. Okay, and the Lagrangian density describes physics at or near one specific space-time point. Okay. So let's say this is my space and time point, t, x, y, z. Okay, so this is one point in my space and time. And the curly L describe actually what happened near this point. It's describe what happened in a local region. That's why it comes from the principle of locality. It's local region. Okay. And near this local region, I can measure my field strength. I can measure my E. I can measure my B. Or equivalently, I can say I define the scalar potential and the vector potential at this point. Okay. So my Lagrangian density should depend on phi and A near this point. Okay. So this phi and A, we get the value near this point, and this would Lagrangian density should depend on that. The Lagrangian density can also depend on the derivative of phi and A. Okay. So derivative of phi and A is also defined in this local region. Okay. And it can also depend on higher order derivatives. I will just write down the first order derivative. Okay. And in addition, the Lagrangian density can also depend on the charge density at this point. It can also depend on the current density at this point. Okay. Oops, sorry. And it can also depend on the derivative of current density and the charge density, etc. Okay. So this Lagrangian density L is a local object. To write down L, I don't need the information far away. I only need to do measurement around this point to decide phi, decide what is A, what is the derivative of phi, what is the derivative of A, what is rho, and what is J around this point. I don't need information far away. So that is the principle of locality. Okay, I only need a local region to define this L, curly L. And if I want to get the total Lagrangian, I just do an integral. Okay. So that is this Lagrangian density. Okay. So let me explain. Let me give one more comment about this principle of locality. Okay. So I told you this principle of locality allows us to have this type of structure. Okay. And what does the principle of locality prohibit us to do? Prevent us from prohibit us to write down. Okay. So for example, as we just said, action can be written as an integral, space-time integral of some local quantity. Okay. So for example, in principle we could have a term like this in our action. Okay. So it's a space-time integral, and this is something local. I got the local charge current density, local charge density rho times the local the scalar potential at that point. So this quantity is totally local. I measure the local charge density, and I get the value of my local scalar potential and multiply them together. This is a local quantity. And then I do a space-time integral and get my action. So this is part of the allowed term in action. And in principle, I can also do this. Okay, I get charge density on this point. So here, instead of scalar potential, I do a derivative of scalar potential. That is also local quantity. So the principle of locality also allow us to have this term. Okay, so as we will show later, in reality, this term doesn't exist. Okay, but in principle, the principle of locality allow us to have such a term. The principle of locality do not allow us to have terms like this. Okay, so as you can see, this term has two spatial intervals, one at x, y, z, another is at a different point, x prime, y prime, z prime. And this term contains information about charge density and x, y, z, and also charge density and x prime, y prime, z prime. Okay, so the x, y, z, rho x, y, z tells me I need to measure charge density here in this point. And the rho x prime, y prime, z prime means I need to measure charge density here in this area. Okay, then I need to multiply them together in this term. Okay, in other words, this term I'm writing down here involves information both here and there. This type of term is not allowed by the principle of locality, because the principle of locality tells us everything is local. Everything I just need to know this local area and I know its contribution to the action. This term requires something non-local. It requires information of both this area and the other area. And these two areas could be separated very far away from each other. That is not allowed. Okay? So the principle of locality do not allow us to have this type of term. It only allows us to have one spatial interval, so that I only need the information about one spatial area for each of the Lagrangian density term. Okay, but this last term we are writing down here require information about two areas in my space, and we need to couple them together. That term is not allowed by the principle of locality. Okay, so that tells us our system has long range coupling, and something here it will influence something happening far away. That is prohibited by the principle of locality. Okay. So let me say one more thing about this prohibited term. Okay, let me bring it up a little bit. Okay. So this is a term that we just mentioned. It's not allowed. It's prohibited by the principle of locality. Okay. If you look more carefully at this term, you will recognize that this term is nothing but the Coulomb's law. Okay. Charge density on one point, charge density on another point, and the numerator is the inverse distance between the 2 points. So in other words, Coulomb's law is prohibited by the principle of locality, which is true, right? So the Coulomb's law tells us if we have charged particle here and if I have charged particle here, and there will be a Coulomb's force between these two particles, okay? And so the charge in one area, say R, will have a long range impact for some charge and some places far away. Okay, so this is actually a violation of the principle of locality. So the Coulomb's interaction actually is a so-called instantaneous interaction. If I move my charge here, the other charge will immediately know the Coulomb's force is changing. Okay, so that one is prohibited by the principle of locality. In other words, Coulomb's law cannot be a fundamental law of physics. It can only be approximation. And indeed, we know this is true. Coulomb's law only works for the so-called electrostatics. Only if the particles are not moving, we can use Coulomb's law to describe the system. And if the charge is moving, then Coulomb's law will be violated. Coulomb's law is not a fundamental principle. And because it violates the principle of locality. Okay? So Coulomb's law, although it's very, very intuitive, it is not allowed in the description of action of electromagnetic dynamics. Okay, so this type of things are not allowed. Okay, so that's the impact of locality. Okay. So the next point I want to bring up is the symmetry. Okay. Symmetry in physics means that if we do something to the system, everything remains the same. So for example, we mentioned earlier on about the rotational symmetry. Okay, so we assume our universe is homogeneous and isotropic. And for isotropic system, no matter I choose x, y, z coordinate this way or this way, my equation of motion and everything should be the same. Okay. What does symmetry mean in this action and vibration principle description. Okay? So symmetry in action means that if we change, say, our coordinate orientation, the action should remain the same. The action should stay invariant. Okay? And the reason for that is actually quite straightforward. Okay, so previously we know symmetry means if we do something, the equation of motion should stay the same. Okay? So all the physics laws and the equation of motion should stay invariant. If you say rotate the x, y, z coordinate, the equation of motion should stay the same. Okay? But equation of motion comes from the action. Equation of motion comes from the variation of action equals 0. Okay? So in other words, saying equation of motion is invariant under some transformation is equivalent to say the action is invariant under some transformation. Okay? So symmetry in the action language is very simple. It just means the action, or say the time interval of the Lagrangian, need to stay invariant, no matter, when we do some symmetry operation to the system. So for example, we learned early on that in our universe, space rotation and the Lorentz transmission should not change equation of motion. Okay? So we have, and we combine them together. This means 4D rotation should not change my equation of motion. Okay? So in the action description, this means 4D rotation should not change my action. My action should stay the same under 4D rotation. So when I do a Lorentz boost, my action should stay the same. Because my action stays the same, the variation of action will stay the same. If the variation of the action stays the same, variation of the action is the equation of motion, so the equation of motion will stay the same. In other words, my action need to be a 4D scalar. Or equivalently, Lagrangian density need to be a 4D scalar. Okay? So my action need to be a 4D scalar. This is a very important constraint. And we will show later, because of this constraint, because of this requirement, we can pretty much write down the action immediately without any freedom to choose the action. Okay, so the action need to be a 4D scalar. Okay. And you probably notice that when I say the action is a 4D scalar, I also mentioned that the Lagrangian density is a 4D scalar. And this is because action equals to integral dt, dx, dy, dz of Lagrangian density, as we mentioned earlier. And this spatial integral, 4D spatial integral, dt, dx, dy, dz, is a scalar. Okay? So we mentioned this in the previous chapter when we define 4D Lorentz boost, etc. Okay? dt, dx, dy, dz is a scalar. It stays invariant under spatial rotation of Lorentz boost. And to see this, it's actually quite straightforward. We can think about the Lorentz boost. Say we do a transformation of the reference frame using velocity along x-axis. Okay, we know if the velocity is along x-axis, dy and dz doesn't change after Lorentz boost, but dt and dx would. And dt and dx, one of them will get a prefactor of gamma. The other one will get 1 over gamma. Okay, so this is a contract of length. So length becomes smaller, contract, but the time becomes longer, time dilation. So the contract of length and time dilation, one is gamma, another is 1 over gamma. They precisely cancel each other. So dt times dx stays the same after Lorentz boost. So this thing is a scalar. Okay, so because this thing is a scalar, S is a scalar, because all the physics laws need to satisfy the relation scalar equals scalar. Okay, so this guy is scalar, this guy is a scalar. It means Lagrangian density must also be a scalar. Okay. So Lagrangian density and the S are both scalars. That's the requirement of symmetry. Okay. Of course, we also have some other symmetry. For example, space invariant. We know that if we take a mirror image of our universe, the physics law should stay the same. That's our assumption. Okay. That's our one assumption about our universe. And we also have the time reversal symmetry. If we flip the arrow of time, things should stay the same. Okay, so this means that action and Lagrangian density should stay the same if I flip r to minus r, and the action and the Lagrangian density should stay the same if I flip t to minus t. In other words, my action should be an even function of space coordinate r. It should be an even function of time t, which means flip t, it stays the same. Okay, so this symmetry actually will help us a lot when we try to write down the action and the equation motion. So that's a symmetry constraint. Let me, okay, here, this notes. Okay, and the last point. So this last point usually is not highlighted in most of the textbooks, but it's actually a very important principle. That is about weak field and slow varying field. Let me explain what do I mean here. So weak field here means I want to consider the situation where my field is small. So I'm drawing in the wrong place on the wrong screen. Okay. So say, for example, if I consider my E and B field, I want my E and B field to be weak. In other words, I want my E and B to be small. Okay. Or if we are using scalar and vector potential, we want it to be small. Okay, and that's what weak field means. Slow varying field, slow varying means this function, say phi, say scalar potential, and the function of t and x, y, z. It changes slowly as the function of time, or x, or y, or z. Okay. So if a function, let's say this is a function f of x, if a function changes very slowly, it means that the derivative of f is small. Okay, slow varying means it's almost constant. The derivative is almost zero. Derivative is small, and it also means that higher order derivatives is even smaller. Okay, so weak field means field itself is small. Okay, so phi is small, my field is small, my field is weak, and this guy is say and if phi is small, oops, sorry, I put it in the wrong way. If phi is small, then it immediately means that phi square is even smaller, and the phi to the third is even smaller, and the phi to the fourth is even smaller. In other words, we can do Taylor expansion and only keep the leading order term. Leading order term means low power, phi or a, to as some low power, as low as possible. Okay, that's a weak field. And the slow varying means the derivative is small, and the second order derivative is even smaller. Third order derivative is even smaller. So I can do a Taylor expansion also for the derivative of the field and only keep lower order derivative. Okay, we only keep the lowest order derivative. Higher order derivative term we will throw away. Okay, so this slow varying and the weak field assumption is actually also a very important assumption, as we will show later. Okay. So we were actually answering our homework, answering our lecture notes. Weak field means that we are going to consider everything very close to zero. E and B are very close to zero, charge density and current density are all very close to zero. And this everything equals zero is my ground state, it's my vacuum state. And I will only consider fluctuations or small deviations from my ground state. That's the so-called low field, weak field, and slow varying approximation. Okay, yeah, this is the same thing as we mentioned. And because of this low field and the slow varying approximation, we know that Lagrangian density, say, is a function of a, phi, and derivative of phi, derivative of a, right? So you probably noticed that early on when I write down this Lagrangian density and the function of phi a, derivative of phi, derivative of a, I didn't write down second order derivative. I didn't write down second order derivative of phi, second order derivative of a. And the reason for that is because of the slow varying. If field is slow varying, second order derivative is much smaller than first order derivative, so I don't need them. They're small, we ignore them. Okay, so this is from slow varying field. And the weak field tells me that phi and a are small. Slow varying tells me derivative phi derivatives a is small. Okay, if these quantities are all small, I can do Taylor expansion. Okay? I can write down the Taylor expansion The leading order term will be a constant term, and we call it A. And then the next order term will be some linear term. So linear term of phi times some coefficient of B1, linear term of A times some coefficient of B2. This B2 should also be a scalar because it has x, y, z coordinates. And there will be some linear term B3 for derivative of phi. There will be some linear term for derivative of A. So that's a linear term. Okay? And there are also quadratic terms, etc., etc., etc. So this slow varying and weak field approximation allow us to write down Lagrangian density as a power law expansion of phi and A and this gradient of phi and gradient of A. The Lagrangian density must take this structure, and this is the reason it must take this structure is because we assume this quantity is small. Okay, so that's the weak field and the slow varying approximation. Okay, that's pretty much all the basic principles that we need. And then we can apply these basic principles to try to write down the action for ENM, for electrodynamics. Okay? So as we know that it should contain 3 parts, the ENM part, the matter part, and the coupling part. So let's first start from the ENM part. Okay? So this is the Lagrangian or the action of the electron and molecule part. Okay? So as we know earlier on, we should write ENM. Actually, sorry, the Lagrangian density of ENM should depend on phi and A. It can also depend on derivative of phi, derivative of A. This derivative includes the spatial derivative and the time derivative. Okay? And we also know that this action or Lagrangian density need to be a scalar, a 4D scalar, a 4 scalar. Because we want everything to be invariant and the Lorentz boost. Okay? And what 4D scalar we can write down out of, say, phi A derivative phi derivative? The most obvious scalar is the following one, is this guy. Okay? So remember, phi over C and the vector potential AX, AY, AZ forms a 4D vector from 4 vector. Okay? As we learned earlier, these 4 quantities together combined together is a 4D vector. And we also learned that if we have a 4D vector, we can do unit product of this 4D vector to itself. Then we get the scalar. And this is a unit product of this 4D vector to itself. Remember, unit product is this 4 vector multiplied by 4 vector with a metric tensor inserted in the middle. Okay? And if we write down this, we calculate, and of course, we can multiply it by some coefficients. And this coefficient we don't know, let me call it alpha. Okay? So this whole thing is a scalar. Okay? And this scalar, if we write down it explicitly, it looks like this. It's a scalar potential phi squared divided by speed of light squared minus the vector potential squared. Okay, so this guy is a scalar, a 4D scalar, a 4 scalar. Okay? So that's the simplest 4 scalar we can get out of phi and A. Okay? And unfortunately, this term is not allowed. Okay? So this term is prohibited. Okay? And from the Lorentz boost point of view, this term is okay. This term is invariant under Lorentz boost. So Lorentz boost is fully happy with this term. Okay. However, this term violates another very fundamental and very important principle, that is a gauge symmetry, or the so-called gauge invariance. Okay, so let me explain that. Okay. As we mentioned earlier on, if we use scalar and vector potential to describe my E and B field, I have a freedom to choose the gauge. Okay. So for example, I can choose phi A to describe my scalar and vector potential, or I can choose another set of scalar and vector potential, which I call phi prime and A prime. Okay? So this new scalar and vector potential, phi prime and A prime, is my old scalar and vector potential plus this quantity. Okay? So lambda here is an arbitrary scalar function of t, x, y, z. And I can take a time derivative, add it to the scalar potential part. I can take a spatial derivative with a minus sign, add it to the vector potential part. And after this transformation is called the gauge transformation. Okay? It transforms one set of scalar and vector potential to another set of scalar and vector potential. And very importantly, both these two sets of scalar and vector potentials, phi A and phi prime A prime, gives the same E and B. Okay? So phi and A and phi prime and A prime don't equal to each other, but they describe exactly the same E and B field. If they describe exactly the same E and B field, everything should stay the same. So this symmetry is called a gauge symmetry. Gauge symmetry means if I choose a different gauge, if I do a gauge transformation, my action should stay the same. My action should stay the same. My action should not change. Because two different gauge choice describe the same E and B field. It should give you exactly the same equation motion and exactly the same everything. Okay? Physics cannot change because I choose different gauge. All the different gauge choices are equivalent to each other. It cannot change. This means the action cannot change if I choose a different gauge. But this term I will write down here doesn't have that, doesn't obey that. If you do a gauge transformation, if you change phi and A to phi prime and A prime, this whole thing will change. This whole thing will change. It will have an explicit dependent of lambda. Okay? It depends on what lambda you choose, you will get different action. Okay? So that is not allowed. Now, if that happens, it tells us that by choosing a different gauge, you will get totally different result and totally different equation motion. So that is the reason why this term is not allowed. Okay. So the bottom line, the simplest possible scalar we can build, 4D scalar we can build from phi and A, violate the gauge symmetry. Okay. So that is not allowed. Okay. So this is a not allowed situation. If phi and A cannot give us a scalar and preserve the gauge symmetry at the same time, we should go to the next order. The next order, if scalar and the vector potential multiplied by scalar and the vector potential itself cannot give us a scalar that satisfies the gauge symmetry, we need to go to next order. Next order means here we need to add one derivative. Okay. So if we add one derivative, we are talking about structures like A, partial A, where this A is for the vector potential, phi and A, 4D vector potential. Let me write down the phi over C here. Okay. So if A mu and A nu, this term is not allowed, then what we need is to go to the next order to add one derivative. Okay. And unfortunately, if we add one derivative, okay, in this structure, there's no way to get a scalar. There's no way to get a 4D scalar. One can prove that mathematically. I will not bother you with the details. I will just tell you the answer. If we add one derivative, so two 4D vector potential and one derivative, no matter how you organize this structure, you can't get a scalar. So this is not allowed either. Oh, by the way, this statement is true for 3 plus 1 dimension. Okay, for 3D space and 1D time, you can't get a scalar of this structure. But if you have 2D spatial, two spatial dimension, 2D system, and one time dimension, you could get such a term. Okay. So such a term is allowed for odd spatial dimension, for even spatial dimension, but not allowed for odd spatial dimension. Our universe has odd spatial dimension 3. So in this situation, this is not allowed. That's not allowed term. Okay, so bottom line, one derivative, there's still no way to satisfy all the symmetry. If one derivative cannot do the job, we need to go to one higher order. We need to get 2 derivatives. So we are talking about terms like this. Derivative of A times derivative of A. Okay. So we'll try to get the scalar of this structure. And we want this scalar is also invariant, also stay the same if we choose one gauge and we transfer one gauge to another gauge choice. Okay. And can we get a scalar out of this structure and also preserve the gauge symmetry? Well, it turns out this is doable, and it's actually very easy. This is because derivative of A, what is derivative of A? Derivative of A is nothing but my 4D tensor of E and B field. Okay? As we discussed early on, if we take the derivative of A and multiply it by a factor of 2, we get a rank 2 tensor. And this rank 2 tensor is nothing but my E and B field strength. Okay, so this derivative of A is actually just E and B. Okay. And this object definitely preserve the gauge symmetry. Under a gauge transformation, if we choose a different gauge, A will change, but E and B will not. So if we use this object, the gauge symmetry is automatically satisfied. Okay? No matter how I change my gauge field, no matter which gauge choice I choose, no matter it's phi A or phi prime A prime, it gives me the same E and B. Okay? So this rank 2 tensor preserve the gauge symmetry. So the gauge symmetry is always satisfied in this guy. Okay? Then the gauge symmetry is satisfied. Then we need to worry about the other. We need to think about the other symmetry, say the Lorentz boost. The Lorentz boost require us to have a scalar in our action. Okay? So basically, the question is, if we are using this object, how do we get a scalar? If I can build a scalar out of this object, then that is a law term in my action. In other words, can we build a 4D scalar out of E and B? Well, you all know the answer. In the previous lecture, we showed that if we have E and B field, if we use E and B field, there are only two scalars we can build. Okay. One is E squared minus B squared. Another one is E dot B. That's only two objects we can build, which is a scalar, and stay invariant under Lorentz boost. We showed this in our lectures, and also you showed this in your homework problem. Okay, so these are the only two scalars we can build, which means for our Lagrangian density, it can only contain two terms. One is E squared minus B squared, another is E dot B. Of course, each of them allows unknown coefficient. I will call the coefficient of the E squared minus B squared term alpha, and the E dot B term I will call the coefficient theta. That's action. And this action is the only action that is allowed by the symmetry. Symmetry here means Lorentz boost, 3D rotation, and combined together as 4D rotation, and the gauge choice, and the gauge symmetry. Okay. So this action, no matter which gauge you choose, you will have the same action. It will not change. Okay. So from the symmetry point of view, the action, we don't have freedom to choose action. Okay. There's no freedom to choose that action. The symmetry is already determining the structure of the action. The only thing that the symmetry do not give us is the value. What is the value of alpha? What is the value of theta? And what is the value of speed of light, c? Okay. We only have these three unknown parameters. In other words, for electrodynamics, everything else, almost everything, are determined by symmetry and the principal locality. From the principal locality and the symmetry, we almost determine everything about the electrodynamics. And the only thing we need to do is to measure three numbers from the experiment. And that three number is alpha, c, and theta. Okay. So this is the power of symmetry and this approach of action. Okay. The power of symmetry and this approach, this action approach, tells us, as long as we know the symmetry, we can almost write down a unique action, a unique theory for our system. And the only thing that symmetry and the theory cannot tell you is the value of some parameters. And in this specific case, we have three parameters, alpha, theta, and c. Experimentally, we just need to measure these three parameters in any experiment. We design some experiment to measure these three parameters. Once these three parameters is determined from the experiment, we know everything about our action. And once we know everything about our action, just take a variation of action, we know everything about the dynamics, the equation, motion, etc. Okay, so that's the power of this approach. Okay, so bottom line, we only need the experiment to tell us what are these three parameters, alpha, theta, and c. Okay, it turns out we can do slightly better than this. Okay? We can do one more step. We can do one more simplification. That simplification is, we can say from theory, we don't need experiment yet. We can say from theory, theta need to be 0. Okay, so instead of three parameters, we need to ask experimentalists to measure. And we can actually tell experimentalists they only need to measure two parameters, alpha and c. That's everything. Okay? The reason we know this theta need to be 0 is also from symmetry. Okay, so we need to consider one or two additional symmetries here. That's the space inversion and time inversion. Let me clear everything. Okay, move it up a little bit. Okay, so here. So let's consider, say, space invariant. Okay. We believe in our universe, space invariant symmetry is preserved. Of course, the standard model tells us that's not exactly the case. There is a very weak space invariant symmetry breaking because of the parity of the neutrinos. But nevertheless, in classical E and M, the space invariant symmetry is preserved. Okay. Space invariant symmetry is preserved means the action need to stay the same if we flip the direction of R, flip R to minus R. And in 505, we already learned that under space invariant, E field should change sign, but B field don't. Okay? If E field changes sign, B field don't, this theta E dot B term will change sign under space invariant. Okay? E changes sign, B doesn't, so the multiplication should change sign. But at the same time, we know the system should have space invariant symmetry. Space invariant symmetry means the action, or say the Lagrangian density, should not change after we do the space invariant transformation. So before we do the space invariant transformation, it's plus theta times E dot B. After we do the space invariant transformation, it's minus theta E dot B. This quantity need to be the same because we want the action to stay invariant under space invariant. Okay, we want before the space invariant transformation and after the space invariant transformation, everything stays the same. One they stay the same. And the only way to make these two quantities equal to each other is to set theta equals 0. There's no other option. Okay? If you want plus theta equals minus theta, then theta can only be 0. Okay? So this is why we know theta needs to be 0 from space invariant symmetry. And we can get the same conclusion from time reversal symmetry. Okay? The story is pretty much the same. Under time reversal transformation, if we flip the arrow of time, as we have learned in 505, E field doesn't change, but B field flips sign. Okay? That means E dot B term flips sign under time reversal. If E dot B term flips sign under time reversal and we want it not to flip sign under time reversal, and to stay the same under time reversal, then the only option is to say theta is 0. This term is not there. Okay? So this is the reason why this term is prohibited by the time reversal and the space invariant symmetry. Okay? So because theta term is not allowed at the end of the day, what we have is a much more simplified Lagrangian density. It's this guy. It just contains one term, E squared minus B squared. And we only need to tell experimentalists to measure two quantities. One is this C, speed of light. Another is this alpha coefficient. Once they measure these two quantities, we know everything about everything about E and M field in other universe. Okay, that's the only thing we need. Okay, so that's the Lagrangian density of E and B field. Okay. So here I do want to mention one small point about this theta term. Okay. So for some of you who are familiar with beyond standard models, you may recognize that this term is actually one of the proposed terms for beyond standard models. Okay, and there, the theta is not a constant. Okay, so in the beyond standard model, so this is a so-called axion field. Okay? So there, this theta in the axion field is not a constant. It's actually a quantity that can vary. Okay? And the variation of that quantity describes the so-called particle, this so-called axion particle, which is candidate of dark matter. Okay? And that axion particle actually is odd under space invariant and time reversal transformation, which means if we flip the direction of arrow of time, the theta field there changes sign. It changes from plus theta to minus theta. That change sign cancels the change sign we have here. So that is why that term is allowed. Okay. The bottom line, in the beyond standard model, you will see a similar object, but there the theta is not a constant. If theta is not a constant, this term is indeed allowed. And there, theta is a fluctuating field and gives you one particle beyond standard model. Okay, that's a so-called theta field. Clear this. Okay, so that's action for the E and M field. Now let's look at the second term of action, the coupling between E and M field and the matter. Okay, as we know that the E and M field we use 4D vector scalar and vector potential to describe the E and M field, and for the matter field we use charge density and current density, which also form a 4D vector. Oh, sorry, I forgot to write here this is actually C rho and the J. Oops. Sorry, this is a typo. I will correct that. Okay. So the E&M field is described by a 4D vector. The charge density, current density is also a 4D vector. Okay. And again, we want the action, or say the Lagrangian density, to be a scalar. Okay. And how do we get the scalar out of these two 4D vectors? Well, the most obvious one is a unit product. This is the unit product between the scalar and the vector potential 4D vector and the charge density, current density 4D vector. And if we write it down, it looks like this. And here, again, we can have some coefficient. We call alpha prime here. The value we don't know. We need to ask experimentalist to measure it. Value we don't know it. Okay. So this is an unknown value. Okay. And this guy is a scalar. And it turns out that this is the correct Lagrangian density. We can check that this term satisfies the space invariant symmetry, satisfies the time reversal symmetry. We can also check this term actually satisfies the gauge symmetry. Okay. It's not very obvious this object stay invariant under gauge transformation, because under gauge transformation, phi and A changes. Okay. If we choose a different gauge, phi becomes phi prime, A becomes A prime. It's not obvious at all this whole thing stays invariant under gauge transformation. Okay. However, it does stay invariant under gauge transformation. We will show that later as we discuss about gauge symmetry and the charge conservation. And later we will learn that this term is indeed okay, stay invariant under gauge transformation, as long as the charge is a conserved quantity. In other words, as long as the charge density and the current density satisfies the continuity equation, this term fully satisfies all the symmetry constraints we have. Okay. Okay. So this is Lagrangian density from the coupling between E&M field and the matrix. Okay, so I think this is a good point to stop. Okay, so in today's lecture, we try to construct the action for E&M field purely based on two principles: principle of locality and symmetry. Okay, so principle of locality tells us we can define Lagrangian density, and this Lagrangian density should only depend on some local quantities like field strength and duality of field strength. Okay. And then we write down and then we use the symmetry guidance to write down the Lagrangian density. Okay, and it turns out symmetry tells us most of the terms are not allowed. Okay? Most of the terms we can imagine will need to be thrown away. So at the end of the day, terms that satisfy all the symmetry constraints is very limited. We only have E squared B squared term, okay? E squared minus B squared term, add this term, scalar and vector potential times charge density and current density. That's only two terms allowed. And we have two free parameters here. Alpha prime, we don't know. We need experimentalist to measure it. And this alpha, we don't know. We need experimentalist to measure it. Oh, and in addition, the speed of light, we don't know. We need experimentalist to measure it. But aside from these three unknown parameters, we need to ask experimentalist to measure. Everything is actually fully decided for E&M field. Okay? As I promised you at the beginning of this chapter, in this chapter, we will pretend that we know nothing about E&M. We don't know Maxwell equation. Okay? And the only knowledge we know about E&M is about symmetries. Okay? And but from the symmetries, just purely from the symmetries and the principle of locality, we find that the action of E&M field has almost no freedom to we have no freedom to choose it. It must look like this structure. And the only freedom we have is the value of these three parameters. The value of these three parameters we cannot fully decide from the theory side or from symmetry. And we need experimental input to determine this three coefficient. But that's the only thing we need. The only input we need as an experimental measurement for these three parameters. Okay, so that's the power of this symmetry and action approach. It gives us a structure of the theory, even if we don't know much detail about the system at all. As long as we know the symmetry, and as long as we know the principle of locality, we can almost fully determine the equation of motion and the theory for very complicated systems. Okay. So in this week's homework, we will deviate a little bit from E&M. So this week's homework has nothing to do with E&M. It is discussed about waves. Okay, and you were sure, and we will study two situations where we don't know the details about the system. We only know the symmetry, and we will show that by only thinking about the symmetry, we can write down a unique action and unique Lagrangian density. And then we will utilize the variation principle to write down the equation of motion. Both those two systems are some systems you are very familiar with, and you have learned it. We have learned it as undergraduate. But in this week's homework, we will study those situations again from totally different point of view, just based on symmetry and the variation principle, say the principle of least action. And from there, you can see that some of the equation of motion, some of the famous equations we learned early on is not accident. We have almost no freedom. We can't change the equation of motion. The equation of motion has to look like that as long as we require proper symmetries. Okay, so I think this is a good point to stop. So in the next lecture, 1 week from today, we will use variation principles to find delta S equals 0 to find the equation of motion for this E and B field, utilizing the action we obtained today. Okay, so this is a good point to start, and I will see you next week.